Hello dear students, welcome. So in yesterday's class we have discussed a little about the digital electronics. There we have seen the analog systems, digital systems, analog signals, digital signals, and also in the digital we have seen a few of the terms where we have seen the base, radix point, place value, weight and all. Okay, and also we have discussed the different types of number systems where I have discussed four types of number systems: binary, decimal, and hexadecimal. These are the three important. Octal I have just discussed it, but it is not there for your syllabus. Okay. So basically, we are focusing on three number systems. That is binary number system, decimal, and hexadecimal. Okay. So these are the important number systems. That is binary number system, decimal number system, and hexadecimal number system. Okay, so yesterday we have studied a little about this. That is, what is the base for this total number of symbols, or base is 2. In the base we have seen the definition that base is nothing but the total number of symbols a number system is having is called as its base. So total number of symbols decimal is having is 10. This is having 16. So we have studied about the bases here, right? So now we'll be seeing the conversions of one number system to another number system. Okay. So what we are dealing today is conversions. Okay. So first in the conversions we will see decimal to other form of conversions. So what will be the decimal to other form of conversion means decimal to binary and decimal to hexadecimal. From decimal to other form of number systems. Okay, decimal is the most commonly used method we'll be using here. Okay, so here we are seeing the decimal to binary and decimal to hexadecimal. Okay, and then we'll be seeing the binary to decimal conversion. Okay, and first we'll see decimal to binary and then binary to decimal type of conversion, and then we'll be seeing decimal to hexa and hexa to decimal conversion. Okay, and later we'll see binary to hexa and hexa to binary. So totally 6 type of conversions we'll be studying here. Okay. So here we are studying the first type of conversion. That is decimal decimal to binary conversion. Decimal to binary conversion. So what happens in the decimal to binary conversion? The binary is having base as 2. Okay, this is having the base as 2. The decimal number that is given to convert into the binary, we keep on dividing by the base, that is the what? 2. Okay. Here, first example I am taking, whatever decimal value is given, any decimal value that is given, we keep on dividing it by 2. And we keep on writing the remainder and question in a manner that we will get a binary number. How to proceed with that, I will be doing now. Okay. For example, I will take a number 24. Okay. I will keep on dividing it by 2 like this. Okay. So when we divide it by 2, it will be 12. Right. 24 is perfectly divisible by 2. That's why it will not give any remainder, that is 0 we have to write here. So here we will write the remainders. We have to write the remainders. Okay. And immediately after each division we will be writing the quotient below. And to the side we will be writing the remainder. Okay. Again divided by 2, we'll get 6. Again, it is not going to give any remainder. So this is 0. Again divided by 2. Okay, 3s are. Again, it is not giving any remainder. Again divided by 2. 1s are, and remainder is also 1. Okay, so this is the binary conversion. We have to read. We have to keep writing the remainders upward to downward. But while writing the final answer in terms of binary, we have to go down to upwards. Okay. Here, this arrow is to just keep on writing the remainders in this form. But while writing the binary number, we have to go down towards up. Okay. So this value 24 base 10. This value 24 base 10 gives what? 24 base 10 is going to give you 1, 1, 000. Okay. Here, this is the binary number. This is a binary number. So a binary number should have what? Only zeros and ones. Okay. This is the conversion for 24 in the form of binary. I will repeat it. Whatever number is given, we have to keep it dividing by 2. We have to write the quotient immediately below the divided, immediately below the value given. Okay, we have to again divide it and keep the value below. We have to keep on putting the values below, whereas the remainders has to be written in front of them. 24 is perfectly divisible by 2. That's why 12 is here, leaving no remainder. Again, 12 is divisible. It gives us 6, and again it is not going to produce any remainder. 6 is also perfectly divisible by 2, that produces 3. So this is also not going giving any remainder. Again, 1s are, but it will give a remainder. Okay, because 2 1s are is 2, but this is 3. 3 minus 2, it is going to give a remainder as 1. Okay, and this is the last divided value. Okay, this is the last quotient that is remaining, that is 1. Now, starting from down to top, we have to write the value, that is 1 1 0 0 0. 1 1 0 0 0 is the binary equivalent for number, decimal number given as 24. Okay, so this is the conversion of decimal to binary. Okay, so here we are seeing a number that is a binary number, that is 1 1 0 0 0. Okay, 1 1 0 0 0. This is a 5-bit value. This is a 5-bit value where this and this, the rightmost bit of the binary value and leftmost bit of the binary value are having some specific names. Okay, this is called as LSB. This is called as MSB. I just want to define these two. Okay, so this LSB is least significant bit. Least significant bit. Whereas this MSB is most significant bit. This is least significant bit and MSB is most significant bit. The rightmost bit is having the position value, otherwise the least weight. This particular value is having 2 to the power of 0, that means 1. Okay, it is having the least weight. This, its position value is the least value. Coming to this will be 2 to the power of 1, 2, 3, this will be 2 to the power of 4. Okay, 2 to the power of 4 means 16, and for this particular 5-bit value, this is having the highest positional value. Okay, this position is having the highest value, that is 16. This is having the value 1. Okay. This will be having the value 2. This will be having the value 4. This will be having the value 8. 2 to the power of 3, 2 to the power of 2, and 2 to the power of 1. Okay. So least significant bit can be defined as the rightmost bit in a binary number. Okay. Rightmost bit in the binary number that is having the least place value. Okay. Whereas most significant bit, what is the most significant bit? It is the leftmost. Okay. If we stand like this is my right hand, rightmost, and this is the leftmost. Okay. So MSB is the leftmost bit in the binary number that is having the highest place value. Okay. These are the two important definitions. Okay. Now we are discussing about the decimal to binary conversion, where this is the decimal number. Okay, how these type of questions could be asked for 2 marks. 24 base 10, write its binary value. Write its binary value. Next time the given value is 24 base 10 and we have converted that value into a base 2 value. 11000 is the base 2 value. Okay. Now moving to the further examples for decimal to binary conversion. So I will proceed with the more examples for conversion of decimal to binary. Okay, so for the next example of conversion decimal to binary, so I'll just repeat the method orally. The given value, whatever value is given, has to be keep on divided by 2. Okay, immediately after the division, we will place the quotient exactly below the given number, and opposite to that number, given number, will be writing the remainder. We keep on dividing it till we get the last question as quotient as 1. Okay, still till that we have to keep on performing the division by 2. Okay, and we have to keep on writing the remainders in front of the quotients we are getting for each step. After getting all the remainders, the last remainder as 1, we have to write them from the down towards the up. Okay, down to up, we have to write the numbers in sequence of one after the other to get the final binary value. Okay. So now I will take another example for decimal to binary conversion. I will take an example of 31, dividing it by 2 each time and writing the remainder here. Okay. So how it is divisible? 15. Okay. 2, 15 are otherwise 15, 2 is 30. What is the value we are having? 31. So it will give a remainder as 1. Right? Again we will divide. 14 we will get 7s are 2 7s are 14 we are going to get. Again we receive a remainder because 14 is the value and we are having 15. So 1 as remainder has to be written here. Again divided, they are going to get what? 3 because 2 3s are 6. But what we are having here is 7. So the value we have got is 7. That is going to give you a remainder as 1. Okay. Again divided by 2. 1s are, and this is 1. Okay. Now the value what we have got is 11 111. So what value? What question is given? Conversion of 31 base 10 to its equivalent binary value that we are having is 11 111. Double one, triple one, base 2. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay, so this is the answer. Here this is called as least significant bit and this is called as most significant. Okay, this is the conversion of decimal to binary conversion. Okay. Now, I'll take another example. I'll take a value as 40. Okay, again which is perfectly divisible by 2. 20, no remainder. Divided by 2. 10s are, no remainder. Divided by 2. 5s are, no remainder. 2s are 4, but remainder will be 1. Again, 2 1s are, there is no remainder. 2 1s are 2 directly it is going. So this is the value 1 0 1 0 0 0. Okay, base 2 1 0 1 triple 0 base 2 is the answer. Okay, so these are the answers. I'll just write these answers here. I will perform the binary to decimal conversion of these numbers itself so that we will remember that we got the values for this. Okay, just the reverse operation is there. This is the value for 31. Okay, I am taking the values which I have already performed for the decimal to binary so that 1 0 1 triple 0, that is 40. Okay, I will take another example. 87. I am taking a larger value, dividing it by 2. This will be 4s and this will be 3s. Okay, 43. Remainder is 1. Okay, 2 43s are 86. Again divided, 2s are 1s are 42. Okay, gives a remainder. Again divided, 1s are that means 2 10s are 20. Remainder is 1. Again divided, 5s are no remainder. 2s are, there is a remainder. 1s are, there is no remainder. Okay. So this is the answer, and the answer is 87 base 10 is 1 0 1 0 1 0 1 1. 1 0 1 0 triple 1 base 3. Okay, so these are the few examples for the conversion of decimal numbers into binary numbers. Here I would like to bring your attention to some important points. Okay. So when we are dividing, we are keeping the quotient here and we are writing the remainder here. I will divide it by 2, I am getting 15. I have a remainder 1, I am placing it. Okay. That is the process, that keep on dividing it, place the values and keep writing the remainders. Okay. So what happens, you have to just observe that you are getting a remainder for every odd number. This is an odd number, this is an odd number, odd number, odd number. Okay, all these 4 are odd numbers are going to give you a remainder. It is just to avoid mistakes while doing the calculations. If at all, in place of writing the remainder as 1, if you place 0, or in place of 0, if you place 1, in that case, you can just cross verify your answer before putting the final answer. There is some hint for it. Okay. See, this is an even number 0, even number 0, even 0, odd 1, even 0. So all the even numbers will give a remainder as 0, whereas the odd numbers will give the remainder as 1. That same thing you can observe here also. Odd 1, odd 1, odd 1, even 0, odd 1, and again even. So keep on dividing by 2, keeping the quotient and placing the remainder in front of the value. While placing, you just observe that we are placing always a remainder as 1 in front of odd numbers and always a remainder as 0 in front of even numbers. Okay. This is one of the clues for otherwise means to maintain a correct answer. Otherwise, the efficiency of the answer you can increase here by just checking it. So what is the value that we are getting? 1010 1010 triple 1, and it is the equivalent of what? 87 base 10. Okay. So this is about decimal to binary conversion, often asked for 2 to 3 marks. Okay. Now we'll do the binary to decimal conversion. I will take the same numbers, what answers we have got from these conversions. I will convert them back to the numbers that we have converted from decimal to binary. Like that, we can also check the value, and we can also learn the new conversion, that is binary to decimal conversion. Okay, so binary to decimal conversion. So we require a binary number here. Okay. Before taking those examples, I will start with the 4-digit number. That is 1011. Okay, base 2. Convert it to its decimal equivalent. So here we have to multiply the number with its place value. 2 to the power of 0 into 2 to the power of 1 into 2 to the power of 2 into 2 to the power of 3. Okay. So the method is the first value 1 into 2 to the power of 3. Okay, that is how to write. 1 into 2 to the power of 3 is nothing but 8. 2 cube. The next value has to be added. 0 into 2 to the power of 2 is 4. That makes nothing but 0 itself. Plus 1 into 2 plus 1 into 1. Okay. This is 8 plus 2 plus 1. That is 11. Okay. So 1011 base 2 is 11 base 10. Okay. Binary 11 is nothing but 1011. Okay. This is the first conversion. Next, I will take the value that we have already computed there in terms of decimal to binary. Okay. The value is 1, 1, 1, 1, 1. Okay. So what we have to do? Into 2 to the power of 2 into 2 to the power of 1 into 2 to the power of 2 into 2 to the power of 3 into 2 to the power of 4. Okay. So 16 into 1 or 1 into 16. Okay. The value 2 to the power of 4 is 16. The value here is 1. Here all the values are 1. So into plus 1 into 16 only I will write the value first and then the place value. First the binary digit, either 0 or 1 is there, that we have to place, and then the place value I am going to take. Okay. Now the next value is 1 into 8 plus 1 into 4 plus 1 into 2 plus 1 into 1. Okay. 16 plus 8 plus 4 plus 2 plus 1. Okay. This makes 10, this makes 26, this makes 30 and 31 is the total. Okay. 8 plus 2, 10, 10 plus 16, 26, 26 plus 4, 30 plus 1, 31. So, what was the conversion we have performed for 31? We got 1, 1, 1, 1, 1. Okay, we got 5 ones. Converting back then to decimal, we got the same value as 31. So, this is the binary to decimal conversion. Let's do another conversion now. So 31 converted into binary gives you 5 ones, and 5 ones converted into decimal gives you back 31. Okay. So we have performed the same on the same value both the type of conversion. 5 ones give you 31 and 31 gives you 5 1. When converted from decimal to binary, it gives you 5 ones, and 5 ones converted to decimal gives you back 31. Okay, so we have seen both the type of conversions here. Decimal value will be having only zeros and 1, and decimal values will be having any symbol between 0 to 9. So all the numbers using 0 to 9 we can form any decimal number. All this we have discussed in yesterday's class itself. Binary number, the binary number will be having only zeros and ones. Okay. So now we'll convert 1 0 1 triple 0 to decimal equivalent, and we'll see if we get 40 or not. Okay. Binary value 1 0 1 triple 0. 1 0 1 triple 0. Convert it to, this is base 2. Find its base 10 value. Base 2 to base 10. Okay. We'll follow the same method. Then we'll be multiplying into its place value. Okay. Into 2 to the power of 0, into 2 to the power of 1, into 2 to the power of 2, into 2 to the power of 3, into 2 to the power of 4, into 2 to the power of 5. Okay. So this is 1, 2, 4, 8, 16, and next will be 32. So it is all the 2 to the power of values. After 32, there will be 64, and then there will be 128, 256, 512, and all. Okay. So for this particular value, we will take the face value 1 into the first one. 1 into 32 plus 0 into 16 plus 1 into 8